Gators, this is 6.5, Interpreting the Behavior of Accumulation Functions Involving Area. Accumulation functions are of this form, and recognize that A is a constant, and recognize that when you take the derivative of this area accumulator, it is the function. Today's lesson will review a lot of what we learned in Unit 5, and we'll analyze the first and second derivative to understand the behavior of this function. Let's take a look and review. This is a function, so we need to understand where to look for increasing, decreasing, relative max, relative min, concave up, concave down, and point of inflection. Does this look familiar? Yeah, when the first derivative is greater than 0, that's increasing. When the first derivative is less than 0, increasing. Relative max is the derivative changes from positive to negative. Minimum, negative to positive. Concave up and down are in reference to the second derivative, and point of inflection is when the second derivative sign changes. So how does that involve f of x? Well, remember, f of x is f prime of x, so we can add a column here and say, hey, instead of talking about capital F prime of x, let's talk about f of x, and all of these things make an adjustment. Okay, let's see if we can go ahead and apply what we've learned on this function. This is, we are looking at g of x, which is the accumulation function. Notice that the graph is not g of x. The graph is f. This is the area, this is the function we're trying to find the area under. It might not be a bad idea for you to take an extra step and do this. Think about this being the derivative of g prime or f, and do a sign chart like I taught you before. And while you're at it, do a sign chart for the second derivative or the first derivative of the first derivative. So let's go ahead and do this. So relative min of g, relative min, now that we have a sign chart, we can tell the relative min will be right here. This is going to be a max, and this is going to be a min, and we'll just estimate it as at relative minimum of g will be we're trying to find x values, so x equal to 5.4 because g prime changes from negative to positive. Now you could have referred to f as well. Relative maximum, this occurs at x equal to 3 because g prime changes from positive to negative. The intervals where g is concave up, we're looking at the second derivative, and it's concave up when it's positive. Remember, this derivative is 0, this derivative is negative, these derivatives are positive, so that'll be the interval from 4 to 6 because g double prime is positive. Intervals where it's concave down, that'll be the interval from 2 to 4, and that's because g double prime is negative. Points of inflection, you can see points of inflection only when the sign changes. That doesn't happen at 2, nor does it happen at 6. So this will be at x equal to 4, and that's because g double prime changes sign. And if you want to do it from negative to positive. Okay, the next one is not asking for the x value, it's actually asking for the maximum value of g. So this is really a y value question. All right, and so it's saying that g of 1 is equal to 5. What is the maximum value of g on the interval from 1 to 5? Well, we know the maximum occurs at right here when the input is 3. So this is an antiderivative, but it's an antiderivative of lots of a family depending on what a is. So this could be lots of things, but we do have a point that we have a reference to. We know at 1 our y value is 5. So over here at 1 when we're looking at 1, we know that when we graph, the antiderivative will be way up here at 5. Now we'd like to find the maximum value, which means I want to get to 3 right here. So what I'm going to do is I'm going to accumulate my area. So if I go from 1 to 2, I'm going to accumulate 2. So now we'll be at 7. And then when I go to 3 and start accumulating more area, this is going to be 1/2 base times height. 1/2 the height times base is 2 times 1/2. That'll be another 1. And if I add another 1, that'll be 8. Now, I only want to get up to this point because this is the point where I know that the maximum value is. So the maximum value is, the max value is 8. Okay, let's take a look at the curve again, and this time we're going to assign g of x to be this area accumulator. It's a little bit more complicated, and this is the graph of f. So we are accumulating area in this. Now remember that this graph tells us this right here. We want to find the value where g has a relative max, and we know the relative max occurs right here. So we want to find the x value, and this is a little bit more complicated because it's just isn't x. So let's first understand that in order to find the relative max, the x value, we know we're looking at the graph here over at 3, and we're looking at when g prime is equal to 0 or f is equal to 0. Okay, so let's go ahead and find the derivative. And that'll be, I'm going to take the derivative of this, and this is a taking derivative of an antiderivative. So this will be f of x over 2 plus 5. Remember, they undo each other, so it's just really the f of this inside the f, and then times by the chain rule, which is 1/2. And we know we want this to be equal to 0. So we want to continue. I'm going to multiply both sides by 2, so this is going to be f of x over 2 plus 5 equals 0. We want to force this expression to be equal to 0. And the only way this expression will be equal to 0 is if this portion right here is equal to 3. So now what I want to do is I want to make x over 2 plus 5 equal to 3 to force this whole thing to be 3. So this is x over 2 is equal to -2, and therefore x is equal to -4. If I put -4 into here, this will force all of this to become a 3, and then f of 3 will be 0. That'll force the derivative to be 0, and then I will have my relative maximum.